In a previous video, we used Binet's formula to generate the terms of a Fibonacci sequence. Well, in this video, we're going to turn the problem around and figure out if we start with a Fibonacci sequence, how could we possibly derive Binet's formula from that? So this is definitely the harder problem. And as a quick reminder, the Fibonacci sequence is a list of numbers where the next term is always obtained by adding the previous two terms. So it can be given by a recurrence relation written like this. And our first two terms are kind of the seeds for the entire sequence. Those are called the initial conditions. And for convenience, I'm going to call these A0 equals 0 and A1 is equal to 1. That's the first two terms in the list. After that, the rest of the terms are generated by the recurrence relation. So if I plug in, for example, n equals 2 into the recurrence relation, I get A2 equals A1 plus A0. And that's 1 plus 0. And that's 1. And I could go to the n equals 3 case. And I could keep doing this as long as I want and get the Fibonacci sequence as far out as I want. Now our goal here is to somehow arrive at this explicit formula that I plug n's into in order to generate the terms in the Fibonacci sequence. And as it turns out, there's a systematic approach to this. This is a special kind of recurrence relation called linear and homogeneous. And more or less, linear means the an's in the formula are raised only to the first power. And homogeneous means there's no extra terms that don't have an's in them, like extra constant terms or functions of n or anything like that. So we look at our recurrence relation for the Fibonacci sequence. It's a simple linear homogeneous equation. All the an's raised to the first power, no extra terms that don't involve an's. And linear homogeneous recurrence relations have a special property that a linear combination of solutions will also be a solution. In other words, a sum of constant multiples of solutions will be a solution. And we're not trying to develop the general theory here. I'm interested in the Fibonacci sequence specifically, so when I write down this fact, what I'm saying is if I find two solutions to satisfy this recurrence relation, then a linear combination of those two solutions will also satisfy it. So we're talking about Fibonacci specifically. So a quick sketch of the proof goes like this. I've already said let an and bn be solutions to the Fibonacci recurrence relation. Then let's examine Cn. It's a linear combination, k1an plus k2bn. But I said an and bn are solutions to the Fibonacci recurrence relation, and that means an can be written as the sum of the two previous terms. And this is also true for bn. And then I gather the n minus 1 terms. And I gather the n minus 2 terms. But that first piece is simply Cn minus 1. I can see if I replace n with n minus 1 in the definition of C, that's correct. The second term is just Cn minus 2. And so we discover that Cn is also following the recurrence relation, that the next term is produced from the sum of the previous two. So this is going to come in handy right at the end of our derivation. And for those of you with a little bit of differential equations experience, this is going to seem familiar. The strategy that we're going to use to find the solution to this recurrence relation is we're going to find some individual solutions, and then we're going to say the most general solution of the recurrence relation is a linear combination of these individual solutions. And then we're going to determine those constants k1 and k2 by plugging in these initial conditions, the first two terms of the sequence. Now we have to find some method to generate solutions to the recurrence relation. And again, this will be familiar to those of you who've taken differential equations. If you haven't taken differential equations, then just think of it as a clever guess. What we're going to do is propose power function solutions to the recurrence relation, and then just follow the algebra and see if it works out. So we propose that our explicit formula that solves this recurrence relation is actually some number r raised to the n power. Then we just substitute that proposal into the recurrence relation, and then we just see what happens. Okay, let's clean this thing up by dividing by r to the n minus 2. That leaves me with r squared equals r plus 1. Well, I can solve this thing and find out what r is. It's just a quadratic equation. So I have r squared minus r minus 1 equals 0. I plug into the quadratic formula, and r is going to be negative b, so that's 1, plus or minus the square root of b squared, so that's 1, minus 4ac, all divided by 2a, so divided by 2. And I end up with something that looks very familiar. Inside that square root, I have 1 plus 4, that's 5. So I have 1 plus or minus root 5, all divided by 2. In other words, there's two different values of r that would satisfy this recurrence relation. And that gives us our two independent solutions of the recurrence relation. And I'll write them as an equals 1 plus root 5 over 2 to the n, and bn is 1 minus root 5 over 2 to the n. And then again, the strategy was to say that the most general solution would be a linear combination of the individual solutions that we found. So this is kind of a general solution to the Fibonacci recurrence relation. And then we determine the k's by plugging in the initial conditions. We want it to start at 0, and we want the next term to be 1. The math is really simple. If I start with c0 equals 0, I plug in n equals 0, and 1 plus root 5 over 2 to the n power just becomes 1. Same thing happens in the second term. Right, c0 is equal to k1 plus k2, and I'm told that that's equal to 0, which means the relationship between k1 and k2 is that they are negatives of each other. And then I plug in c1, and I'm going to plug in the fact that k2 is negative k1. And I factor the k1 out, and I can see that I'm going to have a 1/2 minus a 1/2. So those are going to cancel. Then I have a root 5 over 2 minus negative root 5 over 2, and that simplifies to root 5. And again, we were told c1 is equal to 1, so all this is equal to 1. And I find k1 is 1 over root 5, and k2 is the negative of that, negative 1 over root 5. Plugging in those constants into my general solution, I arrive at Binet's formula. So that's not exactly the way I wrote it when we originally started the video, but I can move the root 5 to the denominator. And now we have an explicit formula where we just sub in n equals 0, n equals 1, n equals 2, and so on. And it will generate exactly the terms of the Fibonacci sequence starting from 0. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.